here we are. We're in Alt Fuels. This is Lecture 6. We're right in the middle of Week 3. And I guess what I'd like to see, and I hope I made this clear in the syllabus, that the, no, not clear in the syllabus? Well, let's go to the syllabus. Let's just revisit the syllabus briefly. So there's just an outline. But what I want to get to is discussion forum grading. So a portion of your grade is based on the discussion forum. And we are in Week 3, and up till now the discussion forum has been okay, but there's nothing here so far. So I'm in the Week 3 discussion. I posted the content, but I haven't heard back on it. So that's one of your checklists for each week. So just wrap that up by tomorrow, please. And then the red dye diesel versus the non-red dye, it's a big deal. Like one of them is a standard that's validated by the Department of Transportation, and the other one is not. It's just kind of your homebrew. As we talked a little bit about last time, how if you're using improper fuel in your engine, you run the risk of damaging it. So that's part of the issue with the red dye. So do some research on that. On Tuesday, I went through the stoichiometry of this problem. So I worked through this problem. This is now posted on the website. It is sitting in one of these two. I did it in one of these two lectures. They're both about 20 minutes long, so have a look at that as well. The Week 3 homework, and I will show the Week 3 homework solution. Just take a peek at that. So I'm just going to make sure it's legible and understandable. So figure 3.3 on page 48. So I'm just going to head right there right now, page 48. Figure 3.3 shows a max yield of about 98% for an alkaline catalyst concentration of 0.7% by weight. And so I'm just looking at that here, and sorry about the lighting, but I think you can probably see it okay. That's exactly where I am in the book. Calculate the amount of lye, sodium hydroxide in pounds, necessary to react with 100 gallons of peanut oil. Use 0.910 grams per cubic centimeter as the density of peanut oil. So based on the problem that I worked on Tuesday, that should be quite doable. So that's the homework for Week 3. It's just this one problem.
So it doesn't have anywhere in the book that would be demonstrated.
Yeah, I had trouble. That's why I had trouble with it too, because it wasn't in the book, I think.
Okay, let's
so
take.
And the practice problem isn't like if there was. I feel like if there was another problem, just like that one, with like maybe an example and an answer of how it's done, and then I guess if you like build on it and then change it a little bit, make it the same, that would make it easier, because it's like it's going cold, doing it cold, and so it's hard to, without getting some like basic ABC. Point A to point B.
Well,
troubleshooting.
Did you guys see the two YouTubes I posted on Tuesday? Because I did the alcohol to oil molar ratio. Well, so the concern is that there's not enough information to do the homework. And my response is whether or not you watched the YouTube video where I solved this problem.
No, I didn't watch that.
Oh, okay, well, that problem, I believe, gives some insight on it, and I'm not going to run through it in detail again, but I will show you where I've covered that.
I mean, I sit and watch that problem too, and I'm still...
You want to, we can go through it again. Yeah, let's just take a look here. This guy right here. So this is the problem that should guide you in the right direction.
Okay.
Okay? So I'll go through it again and just stop me if something doesn't make sense. Okay. So the first thing to probably realize, and I'll just get a
where's the question at first?
this is
Can you do that with my little tablet? You can do that. I wish we could do that with the desktop or laptop, where you put them side by side.
well, you can follow along and just pop that into your notes.
Okay.
And frankly, I always find it's easier for me to really get it if I'm following along, writing along as I'm following.
Okay.
So try that strategy. So let's get back. The week 3 example problem is here. It says indicates that 3 moles of alcohol is the theoretical amount necessary for the biodiesel reaction. And that is, it's right there on page 45. Right there at the bottom of page 45.
That's transesterification?
That's transesterification, yep.
The ester and the alcohol combined?
The triglyceride and the alcohol are combined, exactly. That's exactly right.
So triglyceride is both alcohol and ester combined?
No, a triglyceride does not have any alcohol in it. The alcohol is added to it right there. So there's the triglyceride.
Is the triglyceride the ester, or are those just 3 distinct entities?
An ester is could be a small component of a triglyceride. Yeah. We can just look that up here really quick. It's just that. Yeah. It's just that double oxygen bond. Yeah. So wherever you see that, you're like, okay, that's an ester bond. You get a carbon, and this carbon could be attached to another carbon. The R just means it's just a side chain. If you think of it as just random links. So the carbon is attached to some group. The ester bond itself is this oxygen that's just to the just adjacent to that oxygen double bond. There's another pretty good example of it.
So triglyceride would just have that compound integrated into its chemical formula?
Yep. Okay. Yep. And what what we're seeing here is the esters that result from this reaction. So the triglyceride is there, it reacts with the alcohol, and then these esters are the resulting molecules. Okay. Okay. So, and as I mentioned on Tuesday, the way to force that reaction to completion is to add additional alcohol to it. because otherwise it just kind of sits there and sits around in chemical equilibrium. So the problem that I worked, which is currently on the previous YouTube, was to show that I've got 1,000 pounds of the triglyceride. And again, this is a pretty heavy molecule. Carbon has a molecular weight of 12. There are 55 of them. Hydrogen has a molecular weight of 1. There are 98 of those. Oxygen has a molecular weight of 16, and there are 6 of those. So we converted the 854 grams per mole into pound moles. So there are 854 pounds of this stuff in a pound mole. And we discovered last time that a mole is just essentially a gram mole. And we decided we would saturate this and go all the way up to a molar ratio of 1 to 8. So for every 1 mole of triglycerides, we're going to add 8 moles of methanol. And this is the, these are just the molecular weights of each of the atoms. And then from there, we said, well, how many pound moles of triglycerides are in this 1,000 pound batch? So there are X pound moles in 1,000 pounds, and we just, one equation, one unknown, there's 1 pound mole in 854 pounds. We just did that straight from the stoichiometry. Solved for that, and we realized in this 1,000 pounds, there are 1.17 pound moles. So from that, multiply your 1.17 by 8 to get 9.37 pound moles of methanol. Now we just have to convert back from pound moles to pounds. Let's just copy that. Yeah, go ahead.
The stoichiometric reaction.
Yeah.
How are you getting this 12, 53, 198, 16, 6?
Sure.
Those are just the number of
Yeah.
Molecules?
Exactly.
So you have to look those up, or you just need those offhand?
Well, I do know those offhand because those are the most frequently used, but periodic table, and let's just do a little bit of chemistry here while we're at it. And I always like just going to the dynamic periodic table.
The dynamic.
Dynamic.
So you can see the temperature.
And there they are. There's carbon 12, there's oxygen 15, there's hydrogen 1, and those are going to be the most common we're going to see in this course. Molecular weights. And so, if I showed you methane, so here's carbon, here's 4 hydrogens. We know that the atomic structure of carbon is 6 protons and 6 neutrons. Oops, turn on W. 1, 2, 3, 1, 2, 4. 6 neutrons in the nucleus, and then 6 electrons sitting out here. The atomic weight of the carbon is in the nucleus. It's 12. Electrons have relatively little mass, but the approximate atomic weight of a proton is 1, and the approximate atomic weight of a neutron is 1. So there's your 12. Then the atomic structure of a hydrogen is just 1 proton and 1 electron, and there's your atomic weight of 1. And so those all bear themselves out in the periodic table. The reason you see hydrogen having a weight slightly greater than 1 is because in a random batch of hydrogen, you're going to have some deuterium. You'll have a few hydrogens in there with an extra neutron. But
so the atomic weight, so atomic number is the number of protons,
yep,
neutrons, and the atomic weight, or it's combined, it is combined. That atomic number is just the protons.
The atomic number is just the protons.
The atomic weight is both neutrons and protons.
Right, right.
All right, and you multiply the atomic number with
The number of,
No, you multiply
number
the
of
atomic
carbons.
weight
weight.
by the number of atoms.
of
So
carbons in
for
the-
this methane,
With the number of protons?
yeah, the atomic weight, the number of protons is the same. So methane, you've got 1 carbon, and you got 4 hydrogens. So the molecular weight just equals 4 times 1 plus 1 times 12 equals 16. So the molecular weight or atomic weight, what have you, of methane is 16. This big honker, 55 carbons, 98 hydrogens, 6 oxygens. If I had 1 mole of hydrogen atoms, it would just weigh 1 gram. If I had 1 mole of this thing, it weighs 854 grams. Much bigger, right? Some of it's hydrogen, some of it's oxygen, some of it's carbon, but 1 mole of this thing almost weighs a kilogram. And we decided last time that 1 mole equals 1 gram mole.
Okay.
We just use the word mole because it's how many atomic units are in a single gram. And it happens to be 2.0 or 6.023 times 10 to the 23rd. It's Avogadro's number. And you can do the same thing between pounds and pound moles. So if you have a pound mole of something, you've got 854 pounds of it. Just as if you have a gram mole, you've got 850, and you could do it with any unit. You know, a kilogram mole, a stone mole, what have you. So, because we know that our units were in pounds. So almost every single chemistry problem is going to look exactly like this, where you know each individual molecule has some kind of mass, and these numbers just tell you how much of each atom is in that molecule. Once you know that, you can get the atomic weight of each molecule. What's up, Tanner?
Not much. Actually found time to make it in.
Fantastic. So, we could do another super simple reaction, and let's just do methane reacting with oxygen. And you can think of it a little bit like a dating game. We know we're going to get CO2 out of the thing, right? So here's carbon, here's an oxygen, here's another oxygen, and then we know we're going to get H2O out of it as well. Here's an oxygen, here's a hydrogen, and here's a hydrogen. These are actually double bonds. Double bonds, single bonds. So you look at this thing, you're like, oh, okay, I'm fine because I got one carbon over here, 1 carbon over here. Good. Carbons are balanced. Well, the problem is I've got 4 hydrogens over here and only 2 over here. So let's add another water. Okay, now my hydrogen's balanced. I've got 4 on each side. How about my oxygens? Well, now I've got 4 oxygens on the right, but only 2 on the left. So I got to add another oxygen. So this is a complete combustion of methane. And we were able to do that very simply, very easily in like a minute and a half. Going back up here, good luck with that. You know, I mean, you could spend a lot of time and draw that whole thing out, but it's much easier just to start with this little kind of picture notation where you can count, one single methane molecule. You can look at a single oxygen molecule, and you know that these are the products. You know that carbon dioxide and water are the only 2 things. Well, you might get some CO. You might get some carbon monoxide. You don't want it. What's that mean? Well, it means you didn't put enough oxygen in. Incomplete combustion. There was not enough. You'd sort of smothered it. And we all know what that. And basically, what happens, and that's how people kill themselves in their garages, because the automobile is consuming all of the oxygen in the garage. Once there's no more, you start making this stuff. That's what kills you. I mean, CO goes into your bloodstream and pretends that it's oxygen. It's not, and you die. So this is just showing this sort of atomic or molecular dating game, if you will, in very simple terms. Hey, how's it going?
This is wind and solar?
Yeah. Well, this is alternative fuels, but come on in. We'll start wind and solar in about 10 minutes. So, guys, is that? That's just getting right on down to the nitty-gritty of how chemical reactions work, and how we need to pair them up. Now, what the book said, instead of just this nice pairing where you've got, and we'll write it out this way, CH4 plus 2O2 yields CO2 plus 2H2O. That's the shorthand, because who wants to sit there and draw stick figures all day? And this is basically the stoichiometric or algebraic form for chemistry. Now, back to the problem at hand. What we've done is say, well, I don't want that 3-to-1 ratio. I'm going to jam a whole bunch more alcohol in there so I can drive the reaction to completion. And how many? Well, I want to hit 8. Because somebody has gone to the trouble of taking this data for me. Some poor scientist was there in his or her laboratory, took this data, published it, and now we don't have to reinvent the chemical wheel, so to speak. Same exact deal with the problem set for problem 3. And I encourage you guys to work together on these homework sets a little bit. Struggle with it. Use the discussion board. That's the beauty of the online education. Throw it out there. What's going on? I don't understand. What figure? What chart? Can somebody walk me through it? So, this problem really epitomizes almost any chemical reaction you will ever encounter. And it's just a matter of realizing that each element has an atomic weight. When you combine them together as molecules, obviously that goes up. You need to just count them and multiply to figure out what the molecular weight is. Once you know that, you can convert between pounds and moles. You do this little molecular dating game, and away you go. And you can you could tell me how many how many pounds or how many grams a mole of water weighed. So, okay. And if you need help, I'm happy to, go through this in my, during my office hours. So anything else we need to cover in alt fuels? I've reopened quiz 2, so take another shot at that. Quiz 3 is open and ready to rock. I'm still waiting on a couple students to submit homework 1 and homework 2. Once those are in, I'll just go over them in detail. And also, by the way, not that it's relevant to anyone in this class, but add drop date is Monday. Typically, it's Friday of week 3, but this week it's Monday of week 4. So, if you want to add or drop the course, and I'm thinking for the 2 guys in the course here I haven't heard from, I might just suggest they drop the course rather than fall behind. We'll see. I'll deal with that offline. So, and I guess I'll just say, on behalf of the class, I'm just going to apologize on behalf of the 2 students that have not submitted their homeworks and exams yet, because I do want to go over those in detail, but I just having trouble showing those solutions until everyone's got their work turned in. Okay, that is it for today. I will see you Tuesday at 1, or if not sooner, I'll be in my office for office hours.